We are surrounded by a wall of pure time. The light from the most distant stars and galaxies has traveled for billions of years just to reach our eyes, creating a bubble of everything we can ever possibly see. This is the edge of the observable universe, and it is the ultimate frontier. By the end of this journey, you will understand not just the science of this cosmic horizon, but the breathtaking theories about what exists in the infinite dark beyond it. We will explore whether our universe is just one bubble in an endless foam of others, and if space itself could be curved into a shape that loops back on itself. What do you believe might be waiting in the unseeable vastness? That sphere is our entire reality, everything we have ever known or ever will. Its radius is not 46.5 billion light-years by accident. That staggering distance is a product of two fundamental truths. First, the universe is approximately 13.8 billion years old, so light from the very first moments has been traveling for that long. Second, and this is the crucial twist, space itself has been stretching and expanding throughout that entire journey. So the source of that ancient light is not 13.8 billion light-years away anymore. The expansion of the cosmos has carried it much, much farther to that current distance of about 46.5 billion light-years. This boundary is called the particle horizon, and it is the ultimate time capsule. Every photon of light, every whisper of radiation that crosses this horizon toward us is a message from the deep past, the cosmic microwave background. That faint afterglow of the Big Bang we can detect comes from a shell nearly at this very edge. When we point our telescopes in any direction, we are not just looking out into space, we are peering back through layers of cosmic history. This leads us to a powerful and necessary assumption in cosmology, known as the cosmological principle. It states that on the very largest scales, the universe looks roughly the same everywhere and in every direction. The matter and energy are distributed with a kind of grand, smooth uniformity. There are no special places and no preferred center. This principle is not just philosophical, it is backed by our observations of the cosmic microwave background and the vast web of galaxies. The structures we see here within our observable bubble are assumed to be a fair sample of the whole, but this is where a profound question takes root. If the universe is indeed uniform, and if what we see is just a sample, then what lies beyond our particle horizon? Does the grand tapestry simply continue with more galaxies, more stars, and more cosmic voids stretching on without end? The cosmological principle suggests it might. Our observable universe, for all its immensity, could be just one room in an infinite mansion. This idea transforms the horizon from a simple limit of our vision into a doorway. It is a threshold separating the known from the unknown, the mapped from the imagined. The finite nature of everything we can ever see sets the stage for a mystery that feels truly infinite. This delay between event and observation is the very fabric of our cosmic experience. Think of that distant galaxy, whose light spent 10 billion years crossing the void to finally land in our telescopes. We are not seeing it as it exists now, a mature island of stars. We are witnessing its infancy, a snapshot from an era when our own solar system did not yet exist. This is the profound truth of the cosmic horizon. It is not merely a wall in space, but a boundary in time. Our vision is forever locked into the past because light, for all its incredible speed, still takes time to travel. The moment the universe cooled enough to become transparent, roughly 380,000 years after the Big Bang, the first photons were set free on their long journeys. The farthest light we can possibly see comes from that moment, forming a shell around us at the particle horizon. Yet the universe has not been sitting still during all those eons of travel. Space itself has been stretching, a relentless expansion that affects the light within it. This expansion does something strange to the light. It stretches its wavelength, shifting it toward the red end of the spectrum in a process called redshift. The farther the light has traveled, the more it has been stretched and the redder it appears. This redshift is our primary evidence for the expansion of the universe, a cosmic fingerprint on every distant object we observe. As astrophysicist Janna Levin has noted, we are prisoners of the finite speed of light, seeing only a fossil record of the cosmos. Our telescopes are time machines, and the horizon is the ultimate limit of how far back we can look. And this horizon is not static. With every passing moment, new light from slightly farther away finally reaches us, so the observable universe grows by about 1 light-year every year. But there is a catch, a consequence of the accelerating expansion of space. While our past light cone expands, the contemporary universe is rushing away from us so quickly that light from galaxies now beyond a certain point will never reach us. Their future light cones and ours will never intersect. This means there are regions of the cosmos filled with galaxies and stars right now that are forever hidden from our view. Their stories will never be part of our observable history. This understanding frames everything we know. It tells us that our entire map of reality is a collection of historical artifacts, a patchwork of moments from different epochs. It forces us to accept that what we see is not all there is, and it plants the seed for a thrilling possibility. If our observable universe is just one fossilized bubble within a much larger, contemporary whole, then what does that larger whole contain? The idea of an infinite universe is not just a grand poetic notion. It is a serious possibility born from our most precise measurements of the cosmos. To understand this, we must look at the shape of space itself. General relativity tells us that the fabric of the universe can be curved by the matter and energy within it, like a heavy ball resting on a stretched sheet. This curvature can take one of 3 forms. Space could be positively curved like the surface of a sphere, eventually looping back on itself. It could be negatively curved like a saddle, flaring outward in a hyperbolic shape. Or it could be perfectly flat like an endless sheet of paper. For decades, scientists have used instruments like the WMAP and Planck satellites to study the cosmic microwave background, that ancient afterglow, searching for tiny imprints that reveal the universe's geometry. The data points overwhelmingly to a flat universe. The measurements show no detectable large-scale curvature. This finding is monumental. A flat universe, according to the mathematics of inflation and general relativity, can very easily be an infinite one. It suggests that the grand tapestry of galaxies we see does not just stop at the edge of our vision. It implies that beyond our 46.5 billion light-year horizon, the cosmos simply continues. More galactic superclusters, more vast cosmic voids, more of everything without end. This is the first great mystery of what lies beyond, the possibility of true infinity. If space is infinite and the matter within it is roughly evenly distributed, as the cosmological principle suggests, then the consequences are staggering to contemplate. In an infinite volume, every possible arrangement of particles governed by the laws of physics will occur, not just once but an infinite number of times. As physicist Brian Greene has explored, this means there could be regions out there where every atom is arranged exactly as it is here on Earth. There could be a perfect copy of our solar system, a perfect copy of you, reading a perfect copy of this script. There could be worlds where history unfolded with subtle differences and realities that are utterly unrecognizable. This concept, sometimes called the inflationary multiverse, transforms the horizon from a simple limit into a veil. It hides from us an expanse where every story that can be told is being told, an infinite number of times over. The philosophical weight of this is immense. It challenges our deepest intuitions about uniqueness and identity. If an infinite number of versions of us exist, what does that mean for the choices we make or the lives we lead? It also presents a cosmic paradox of loneliness and connection. We are forever isolated within our finite, observable bubble, yet theoretically connected to an infinity of reflections in the unseeable beyond. This idea of endless repetition feels both comforting and profoundly unsettling, a mystery that stretches the mind as far as space itself might stretch. But infinity is not the only possibility waiting in the dark. A second, even more radical mystery emerges from the leading edges of cosmology and theoretical physics. What if our entire cosmos, from horizon to horizon, is not the whole story, but merely a single bubble in a frothing, boundless sea of other universes? This is the multiverse hypothesis, and it represents a complete reimagining of reality itself. The idea springs from our most successful theories, like cosmic inflation. This theory explains the universe's remarkable smoothness and flatness by proposing a period of unimaginably rapid expansion in its first fleeting moments. Some versions of inflation, particularly the concept of eternal inflation, suggest this explosive process never truly stops. Instead, it continues forever in a background sea of energy, with random quantum fluctuations occasionally causing pockets of that energy to decay. Each of these decaying pockets stops inflating and cools down, forming what we would call a separate universe, a bubble with its own Big Bang and its own distinct spacetime. Our entire observable cosmos could be just one such bubble. Cosmologist Andre Lind, a pioneer of this idea, describes it as a grand multiverse ensemble, where new universes are constantly budding off from an eternally inflating background. In this view, the space beyond our cosmic horizon is not just more of our universe, it is a chaotic foam of other universes, each with potentially different physical laws and fundamental constants. This leads us to another profound framework, string theory. In its attempt to unify all forces of nature, string theory suggests the existence of extra, tiny dimensions of space curled up at every point. Some versions propose that our universe is a three-dimensional membrane, or brain, floating within a higher dimensional bulk. Other brains could exist parallel to ours, mere millimeters away in a dimension we cannot perceive. These brain worlds could be other entire universes, occasionally interacting with ours in ways that might explain cosmic mysteries. Then there is the quantum many worlds interpretation, which comes from a different direction entirely. It suggests that every quantum event with multiple possible outcomes causes reality to split, creating a branching tree of parallel universes where every possibility is realized. While this is a different kind of multiverse, it adds to the overarching theme that our reality may be one thread in an inconceivably vast tapestry of possibilities. This multiverse landscape offers a potential answer to one of cosmology's deepest puzzles, the fine-tuning problem. The laws and constants of our universe, like the strength of gravity or the mass of an electron, appear exquisitely balanced to allow for stars, planets, and life. The odds seem astronomically against it, but if there are an infinite number of universes with different settings, then it is no surprise that we find ourselves in one of the rare, habitable ones. While these ideas are currently beyond the reach of direct experimental proof, they push the boundaries of thought. They ask us to consider that what lies beyond the edge is not just more space, but entirely different realms of existence, each with its own history, its own physics, and perhaps its own forms of life. The horizon becomes not just a limit of sight, but a wall between worlds. Yet another possibility redefines the very meaning of beyond. What if the universe is not infinite, but instead folds back on itself in a complex, closed shape? This is the mystery of cosmic topology, the study of space's global geometry and connectivity. Think of the classic video game where a spaceship flying off the right side of the screen instantly reappears on the left. The screen is finite but has no boundary it wraps around. Our universe could operate on a similar but three-dimensional principle. We have already seen that measurements indicate a flat local geometry, but that does not rule out a shape that is flat overall yet connected in a surprising way. Imagine taking a flat piece of paper and rolling it into a cylinder. The paper itself is not curved, but its ends are joined. Now, imagine joining the ends of that cylinder to form a donut shape or torus. In 3 dimensions, this becomes a 3-torus, a room where if you travel far enough in one straight line, you would eventually return to your starting point from the opposite direction. The universe could be finite, yet completely unbounded, with no edges or exterior at all. Mathematician Jeffrey Weeks, who has dedicated his career to visualizing such shapes, offers a compelling thought. The universe could be finite but so vast that light simply has not had time to loop all the way around and show us repeats. In such a cosmos, what lies beyond our observable horizon is not some other place. It is simply more of the same connected space, eventually wrapping back to us. This idea leads to a breathtaking search for evidence. If space is multiply connected, the ancient light of the cosmic microwave background might reveal subtle fingerprints. We could see matching circles, patterns in the sky that are identical because they are actually images of the same distant region, seen from 2 different directions as the light wrapped around the cosmos. Another candidate shape is the Poincare dodecahedral space, a beautifully symmetric, finite volume where the universe is modeled on a 12-sided shape, like a cosmic soccer ball. While such patterns have been sought, definitive proof remains elusive, leaving this as one of the most elegant unsolved puzzles. The philosophical implications are profound. A finite, wrapped universe means everything that exists is contained within a single, self-contained entity. There is no outside, no beyond in the traditional sense. The entire cosmos becomes a kind of cosmic Möbius strip, a closed loop of reality. This transforms the journey from a voyage into an unknown exterior into an exploration of an immense, but ultimately knowable, interior. It suggests a universe that is not sprawling endlessly, but is instead complete, whole, and perhaps even comprehensible in its totality. The horizon then becomes not a wall, but a doorway into the next segment of the loop, a segment whose light is still on its way back to us. This relentless expansion brings us to the most dominant force shaping our cosmic horizon, dark energy. It is not a substance in the familiar sense, but a property of space itself, a repulsive force that makes up roughly 68% of the entire cosmos. Its discovery in the late 1990s, through observations of distant supernova by teams led by scientists like Adam Rees, was a shock that redefined our cosmic story. We learned the universe is not just expanding, it is accelerating. Galaxies are flying apart faster and faster with each passing moment. This acceleration has a direct and profound effect on our view of the cosmos. As Adam Rees has explained, dark energy is causing the universe to expand at an ever-increasing rate, pushing the cosmic horizon further away. Think of it like this. Imagine you are on a raft in the middle of an ocean that is stretching. The farther another raft is from you, the faster the expanding ocean carries it away. At a certain distance, that raft is moving away faster than any wave you could send could travel toward it. That is exactly what happens with light. Galaxies beyond our cosmic horizon are receding from us faster than the speed of light itself, not because they are moving through space, but because the space between us is stretching so rapidly. Their light, no matter how bright, can never overcome that expansion to reach us. They are lost to our view forever, their stories eternally untold within our observable bubble. To explain this mysterious force, physicists turn to 2 leading theories. The first is Einstein's cosmological constant, a kind of built-in energy of the vacuum of space that acts as a constant, gentle push. The second is a dynamic field called quintessence, which could vary over time and space, changing its strength. Both attempt to describe the engine behind the acceleration, but its true nature remains one of the greatest unsolved puzzles in science. The influence of dark energy suggests that beyond our horizon, the expansion is not just continuing, it is winning. It paints a future where the isolation of our cosmic island becomes absolute. In one possible scenario, the acceleration becomes so powerful it overwhelms all other forces in a cataclysmic event theorists call the Big Rip, tearing apart galaxies, stars, and even atoms themselves. In a gentler but no less lonely fate, the acceleration could lead to eternal dilution, where galaxies beyond our local group vanish over the horizon, leaving our night sky empty of all but the closest stars. Understanding dark energy is therefore not just about a force, it is about mapping the ultimate fate of everything we see and determining what vast regions of reality are destined to remain forever hidden, their existence inferred but never confirmed. This force actively sculpts the boundary of our knowledge, deciding what gets included in the story of our universe and what is exiled to the unseeable beyond. The sheer variety of these possibilities points toward a deeper, more fundamental mystery about our cosmic origins. To grasp it, we must return to the very beginning, to a fraction of a second after the Big Bang, and to a concept that reshaped our understanding of how everything began: cosmic inflation. This theory, pioneered by physicist Alan Guth, proposes that the universe underwent a period of unimaginably rapid, exponential expansion in its first fleeting moments. This sudden growth spurt explains the remarkable smoothness and large-scale flatness we observe today. But the most profound implication of inflation is not how it started, but how it might never have stopped. This leads us to the possibility of a chaotic inflationary landscape. Imagine the primordial cosmos not as a single, uniform fireball, but as a seething, turbulent sea of energy. In this roiling meta-universe, inflation could be an eternal process. Random quantum fluctuations act like seeds, causing pockets of this energetic field to suddenly decay and settle down. Each of these decaying pockets stops inflating, cools, and becomes what we would recognize as a separate universe, with its own Big Bang and its own distinct spacetime. Our entire observable cosmos, with all its hundreds of billions of galaxies, could be just one such smooth, stable patch within a wildly irregular and vastly larger structure. As Alan Guth himself has suggested, eternal inflation could produce an infinite variety of pocket universes. In this chaotic landscape, different regions stopped inflating at wildly different times. Some domains may have crystallized into universes with physical laws and fundamental constants completely alien to our own. Others might still be inflating at a furious rate, creating immense, empty voids between the islands of reality like ours. Beyond our particle horizon, we might not simply find more galaxies like our own. We could, in theory, encounter the border of another inflationary domain, a region where physics operates in bizarre and unfamiliar ways. These domains would be eternally separate from us, walled off by zones of space that are still inflating faster than light can cross them. This vision transforms the cosmos into something like a fractal, an endlessly creative and varied structure where every stable pocket is a unique cosmic experiment. It implies a level of diversity and complexity that dwarfs our local, orderly universe. The grand tapestry is not just woven with different threads, it is made of entirely different kinds of cloth. While we are forever confined to our own smooth patch, the theory suggests we are surrounded by a hidden menagerie of other realities, their light and stories forever barred from reaching us by the relentless, inflationary walls of spacetime itself. Yet another profound mystery redefines the very nature of time itself. Our cosmic story might not be a single, linear narrative with one beginning and one end, but an eternal, repeating cycle of birth, death, and rebirth. This is the vision of a cyclic or bouncing universe where the cosmos is a cosmic phoenix, endlessly rising from its own ashes. In these models, championed by physicists like Paul Steinhardt and Neil Turok, the Big Bang was not the ultimate beginning. It was instead a moment of transition, a great bounce from a prior phase where the universe was contracting. What lies beyond our observable universe, in a temporal sense, could be an entire previous cycle, a completely different epoch of existence with its own history, its own galaxies, and perhaps its own forms of life. As Steinhardt has suggested, the universe may have no beginning and no end, just eternal cycles. This idea challenges our deepest intuitions about creation. It replaces a singular origin point with an infinite, rhythmic dance of expansion and contraction. How could such a bounce be possible without everything collapsing into a destructive singularity? Some theories propose that the immense energies involved as the universe contracts could trigger quantum gravity effects, a realm where our current laws of physics break down. This quantum realm might act like a cosmic trampoline, repelling the collapse and initiating a new expansion. Another compelling framework comes from string theory and the concept of brane worlds. Imagine our three-dimensional universe as a membrane floating in a higher dimensional space, parallel to another brane. These two worlds could periodically collide, with each collision releasing immense energy that fuels a new Big Bang and a phase of expansion. The universes then drift apart, only to be drawn together again by forces across the higher dimension, setting the stage for the next collision billions of years later. In this breathtaking scenario, what lies beyond our cosmic horizon is not just more space, but the entire timeline of a sister universe, destined to meet ours again in a future cosmic dawn. This cyclic model offers elegant solutions to some of cosmology's thorniest puzzles. It can naturally explain the smoothness and flatness we observe as each bounce stretches and resets the cosmos. It also provides an alternative to the need for a mysterious inflationary epoch, framing it as a consequence of the bounce itself. The philosophical implications are staggering. It suggests that time is not a river flowing in one direction, but an ocean with eternal tides. Every ending contains the seed of a new beginning. If true, then our universe's current expansion, its galaxies and stars, are merely one act in a play that has been performed an infinite number of times before and will be performed an infinite number of times again. The horizon we peer into is not just a boundary of sight, but a window into a deeper rhythm, a heartbeat of reality that pulses across eons we can scarcely comprehend. These cycles of cosmic rebirth lead us to the ultimate temporal frontier. We have looked beyond the edge in space, but what about the edge in time? What existed before the Big Bang? This question pushes us toward a seventh mystery, the nature of the pre-Big Bang universe, a realm forever beyond our observational horizon, not in space, but in the direction of the past. Our current laws of physics break down at the moment of the singularity, creating a veil over all that came before. To lift that veil, we must venture into the domain of quantum gravity, where theories propose astonishing possibilities for a state that preceded our cosmic dawn. One compelling idea comes from loop quantum cosmology, an offshoot of loop quantum gravity. It suggests there was no true singularity, no point of infinite density. Instead, our expanding universe could have been preceded by a great bounce from a prior contracting phase. In this view, what we call the Big Bang was a moment of transition, a cosmic springboard. The universe before it was collapsing under its own gravity, but as it reached an immense but finite density, quantum repulsive forces kicked in, reversing the collapse into the expansion we see today. This creates a bridge across time, implying that our universe has a history that extends backward before time zero. Another framework, string gas cosmology, proposes a different starting point. It imagines the early universe as a hot, dense, and nearly static soup of the fundamental strings from string theory. This chaotic, high-energy state could have existed for an eternity before a random fluctuation triggered a rapid expansion, setting off the events that led to our familiar cosmos. Perhaps the most profound and elegant vision comes from renowned physicist Roger Penrose and his conformal cyclic cosmology. Penrose proposes a breathtakingly beautiful, yet almost incomprehensible, link between the unimaginably distant future and the beginning. In his model, as the universe expands forever and all matter eventually decays into radiation, the distinction between particles and photons, between objects and the space between them, completely vanishes. The universe becomes a smooth, featureless sea of energy where the concept of scale loses all meaning. At this point, Penrose suggests, this distant future state can be mathematically conformally rescaled to become the high entropy, smooth starting conditions for a new Big Bang. In this cyclical scheme, the distant future of one universe becomes the Big Bang of the next. Each cosmic eon is separate, yet connected through this transcendent transformation. What lies beyond our beginning, then, could be the faded, timeless end of a previous cosmic eon, its black holes having evaporated and its stars long gone, leaving only a ghostly imprint of radiation that might, as Penrose suggests, even be detectable in our cosmic microwave background. These theories force us to redefine existence itself. The pre-Big Bang state might have operated under entirely different physical laws, a regime where time and space as we know them did not yet exist or were woven from a more fundamental fabric. Exploring these ideas is not just speculation, it is the necessary work of pushing physics to its limits, requiring new theories of quantum gravity to describe the transcendent conditions that birthed our reality. It asks us to consider that our entire cosmic story, from the first stars to the last black holes, might be just one chapter in an eternal book, where the final page of one volume seamlessly becomes the blank first page of the next. The cosmic web we can map is already a tapestry of staggering scale and beauty. From our vantage point, we see galaxies strung along immense filaments, gathered into colossal superclusters and separated by vast, nearly empty voids. This is the large-scale structure of our observable universe, a pattern born from tiny quantum ripples in the infant cosmos, stretched to cosmic proportions by inflation. Our own galactic home is part of the Laniakea supercluster, a gravitational metropolis containing hundreds of thousands of galaxies, spanning over 500 million light-years. As astronomer Brent Tully describes it, Laniakea is our local continent in the cosmic geography. But here is a compelling thought. If the universe extends far beyond our observable horizon, and if the initial seeds of structure were not perfectly uniform, then the patterns we see may only be a local sample of a much grander design. What larger, more magnificent assemblies might exist in the unseeable realms? The cosmological principle suggests that on the very largest scales, things should average out to uniformity. Yet, some cosmological models allow for the possibility of giant fluctuations, rare but possible deviations in the density of matter from the early universe. Imagine a region where, by chance, those initial quantum seeds were significantly more pronounced. Beyond our horizon, there could exist an overdensity so immense it makes Laniakea look like a neighborhood. A supercluster, a gravitational titan pulling thousands of superclusters into its orbit, forming a structure on a scale that would redefine our understanding of cosmic architecture. Conversely, there might be a void of truly epic proportions, a billion light-year expanse of near-nothingness, a desert so vast and empty that the galaxies on its far side are forever isolated from our own. The existence of such structures would not just be a curiosity, it would have profound implications. These unseen giants would exert a gravitational pull on everything within our observable bubble, a subtle tug that could influence the motion of galaxies on our fringes. We might one day infer their presence indirectly by detecting a mysterious flow of thousands of galaxies moving in unison toward a point on the hidden side of our horizon, pulled by the immense gravity of something we can never see. Furthermore, if different physical conditions prevailed in distant domains, as some multiverse theories suggest, we might even speculate about regions dominated by forms of matter or energy that are exotic and unfamiliar. While this remains in the realm of theory, it underscores a thrilling possibility that the grandest patterns of the cosmos, the true backbone of the cosmic web, may lie forever just out of sight, waiting to be deduced not by light, but by its ghostly gravitational shadow on all that we can see. The cosmic web's hidden giants lead us to a mystery that is profoundly human in its curiosity. If the universe is truly vast beyond our horizon, filled with countless galaxies, then surely it must also be filled with countless possibilities for life. This brings us to the potential for alien civilizations and the staggering thought that their greatest works might be unfolding in realms we can never see. The famous Fermi paradox asks a simple, haunting question: if intelligent life is common, where is everybody? Our telescopes have scanned the skies for decades, listening for radio signals, looking for signs of technology, and finding only silence. One compelling answer to this great silence is the cosmic horizon itself. Perhaps we are not alone, but simply isolated. Advanced civilizations, if they exist, may be concentrated in galaxies or superclusters that lie permanently beyond our particle horizon, their light and signals forever unable to reach us due to the accelerating expansion of space. They are not hiding, they are simply exiled by physics from our observable bubble. Within our own bubble, we search for technosignatures, evidence of technology like city lights on exoplanets or massive artificial structures. The most famous theoretical construct is the Dyson sphere, a hypothetical shell built around a star by a civilization harnessing all its energy. While we have found no definitive evidence of such things, the search continues, scanning starlight for unusual dips or infrared signatures that betray vast engineering. But as astrobiologist Caleb Scharf has speculated, a sufficiently advanced civilization might manipulate spacetime itself, creating signatures invisible to us. Their artifacts might not be solid shells of metal, but gravitational lenses, manipulated black holes, or phenomena that blend seamlessly into the background of the cosmos. Their greatest achievements might be indistinguishable from natural astrophysical events, at least to our current level of understanding. This idea transforms the darkness beyond our horizon from an empty void into a canvas of potential. In those unseen domains, the density of intelligent life could be far higher. Galactic empires might rise and fall, cosmic-scale art might be created, and philosophies might be forged under alien suns, all in a parallel narrative to our own that we are completely unaware of. Their technologies might even allow them to perceive or interact with the multiverse or higher dimensions in ways we cannot yet fathom. This mystery beautifully blends cosmology with astrobiology. It suggests that what lies beyond the edge might include not just natural phenomena like exotic matter or different physical laws, but also the products of intelligence and culture. The ultimate frontier could be waiting not just with new physics, but with new neighbors, their stories waiting in the darkness for a future epoch when, perhaps, the expansion of the universe slows or new physics allows for a form of contact we cannot yet envision. Our search for neighbors in the dark leads us to perhaps the most radical reimagining of reality on the list. The 10th mystery suggests the universe itself might be a cosmic illusion, a hologram. This is not science fiction, but a serious proposal born from the desperate need to unite quantum mechanics and gravity. The holographic principle, emerging from the study of black holes, makes an astonishing claim. All the information needed to describe everything within a volume of space, every star, every planet, every thought, could be entirely encoded on its two-dimensional boundary. Think of a credit card hologram, a flat sticker that creates the illusion of a three-dimensional object. Now scale that idea to the cosmos. Our rich, three-dimensional reality, with its depth and texture, might be a projection from a vast, thin shell of information at the very edge of our observable universe. Physicist Juan Maldacena provided a groundbreaking mathematical model for this, known as the AD-SCFT correspondence. It demonstrates a precise equivalence between a gravitational theory in a hypothetical anti-de Sitter space and a conformal field theory, a quantum theory, living on its lower dimensional boundary. While our universe is not precisely described by this model, the principle it reveals is electrifying. It hints that a complete description of our cosmos might not require us to model the infinite interior at all. Instead, everything could be written on the cosmic horizon itself. The particles, the forces, the very fabric of spacetime we experience could be emergent phenomena, like the ripples and patterns on the surface of a pond that arise from the collective motion of countless unseen water molecules. If this is true, then the question of what lies beyond the observable universe undergoes a profound transformation. Beyond is not a place containing more galaxies. Instead, beyond might be a more fundamental, perhaps simpler, layer of information. The three-dimensional expanse we perceive could be the output, while the real computation happens on the two-dimensional screen of the horizon. This idea turns our intuition inside out. We are not looking out from a center to a distant edge. We are, in a sense, living on the inside of that edge, experiencing a grand projection. It suggests that the ultimate laws of physics are not written in the language of volumes and forces as we know them, but in the language of information density and quantum entanglement on a surface. While applying this directly to our expanding, flat universe remains speculative, the implication is staggering. It means that to understand the deepest structure of reality, we might not need to peer past the horizon at all. We might simply need to learn to read the code written on its surface, a cosmic cipher holding the blueprint for everything within. This holographic vision of reality brings us face to face with a timeless human dilemma. We are a species built to explore, to push boundaries and map the unknown. Yet physics itself has drawn a final frontier we may never cross. The edge of the observable universe is not just a scientific fact, it is a profound philosophical mirror. It reflects our deepest yearning for understanding, while confronting us with the possibility of a fundamental, permanent limit to what we can ever know. Centuries ago, the philosopher Immanuel Kant distinguished between the world as it appears to us, the phenomenal world we can measure and observe, and the world as it truly is in itself, the noumenal world which may forever remain beyond our perception. Modern cosmology has given this abstract idea a concrete cosmic scale. Our entire observable universe, with all its billions of galaxies, might be just the phenomenal world, the appearance. What lies beyond the particle horizon could be the ultimate noumenal realm, the thing in itself eternally veiled. This presents a staggering question. Can a universe that contains conscious observers like us ever be fully understood by those very observers? Or are we, by our very nature as products of this cosmos, forever trapped inside a bubble of perception, decoding shadows on the wall of a cave whose true extent we cannot fathom? This challenge touches the search for ultimate purpose. If the cosmos is infinite, or a multiverse of endless variations, does that render our local story meaningless, or does it make the fragile emergence of life and consciousness in our particular bubble all the more precious? If the universe is finite and wrapped, a self-contained whole, does that suggest a kind of cosmic completeness, a designed elegance? Science cannot answer these questions of meaning, but it frames them with breathtaking clarity. The very laws that allow stars to shine and minds to wonder also conspire to hide the totality of existence from our view. This is not a failure, but a feature of our condition. The unknowable beyond serves as a perpetual reminder that wonder and mystery are not temporary states to be solved and discarded, but essential engines of curiosity. They drive us to build better telescopes, to devise more elegant theories, to look deeper into the cosmic microwave background for clues. The struggle to comprehend the incomprehensible enriches our intellectual and spiritual journey far more than any final answer ever could. In the end, the greatest discovery at the edge of everything may not be a new particle or a hidden dimension, but a deeper understanding of our own place within the grand narrative. We are the universe becoming aware of itself, yet that self-awareness is confined to a single, glowing chapter of a story whose full title we may never read. And perhaps that is exactly what makes the story worth telling. The sky was not always a window to infinity. For most of human history, it was a ceiling. Ancient civilizations gazed upward and saw not a boundless expanse but a structure. The Egyptians envisioned the goddess Nut, her star-studded body arched over the earth. Mesopotamian myths described a solid dome holding back a celestial ocean, with the sun, moon, and stars fixed upon it. In these cosmologies, the universe had a clear, tangible edge, a boundary between the ordered world below and the chaotic, divine waters above. These were not primitive guesses, but profound attempts to make sense of the cosmos from a profoundly limited vantage point. They placed humanity at the center of a comprehensible, if small, creation. The very idea of looking beyond that dome was not a scientific question, but a theological or mythological one. What lay outside was the realm of gods, of creation itself, a mystery that belonged to story and faith. This perspective held for millennia a comforting enclosure that defined reality. Then a crack appeared in the celestial sphere. In the 16th century, Nicolaus Copernicus proposed a radical rearrangement, moving the sun to the center. This was more than a shift in planetary orbits. It was the first great push against a bounded cosmos. If Earth was not the center, then perhaps the heavens were not organized around us either. The universe began to grow, but it was a philosopher, not an astronomer, who dared to take the next, most dangerous leap. Giordano Bruno looked at the Copernican model and saw not just a new solar system, but a new principle. He proposed that the stars were other suns, each potentially circled by other worlds, and that this multitude of systems stretched on without end. He envisioned an infinite universe with no center and no edge. For this heresy against the doctrinal view of a finite, created cosmos, he was tried by the Roman Inquisition and burned at the stake. Bruno's fate is a stark reminder of how threatening the idea of the infinite could be, challenging not just science, but the very foundations of religious and philosophical authority. His sacrifice, though tragic, planted a seed. The invention of the telescope soon turned philosophical speculation into observable fact. Galileo's lenses revealed mountains on the moon and moons around Jupiter, proving the heavens were not a perfect, immutable shell. The celestial sphere was shattered. The universe kept expanding in the human imagination. Isaac Newton provided a framework of universal gravity that worked equally well in an infinite void. The static, eternal universe of the 18th and 19th centuries was in many ways infinite and featureless, yet it was still a universe without a story, without a history. The true revolution came in the 20th century. Edwin Hubble's discovery that galaxies are flying away from each other revealed a cosmos that is dynamic and evolving. The Big Bang Theory gave our universe an origin, a history, and crucially, a visible horizon. The modern cosmic horizon, that shell of ancient light, is the successor to the mythical dome. It is a boundary not of stone or water, but of information and causality, set by the finite speed of light and the age of the universe. This journey from a solid sky to an expanding frontier of time shows a clear pattern. Each time we thought we had found the final edge, we discovered it was merely the limit of our current understanding. The dome gave way to the planetary spheres, which gave way to the infinite Newtonian void, which itself gave way to the expanding universe with its particle horizon. Our ancestors used myth to explain what they could not see. We now use physics. Yet the impulse is the same, a deep human need to map the limits of our world and to wonder what lies just beyond them. This historical arc suggests the most hopeful possibility of all, that our current horizon, for all its scientific rigor, is also provisional. It is the latest model, not the final map. Just as Bruno's infinite cosmos was once an unthinkable heresy, our concepts of dark energy, the multiverse, or cosmic holograms may one day be seen as stepping stones to an even grander, more bewildering reality. The past teaches us that the only constant is the expansion of our imagination against the perceived edges of the possible. Our understanding of the cosmic horizon is not built on philosophy alone, but on precise, painstaking observation. To map the very edge of everything we can see, astronomers have constructed a new generation of eyes, instruments that peer into the deep past by collecting the oldest light in the universe. The Hubble Space Telescope, orbiting above the distorting blanket of our atmosphere, has been our premier time machine for decades. By staring for days at what appears to be empty space, Hubble's deep field images revealed thousands of faint smudges, each a galaxy as it existed billions of years ago. These are not the majestic spirals we see nearby, but chaotic, infant galaxies caught in the act of formation. Hubble showed us the universe in its youth, providing a direct visual record of cosmic evolution stretching back over 13 billion years. But to see the universe in its infancy, mere moments after its birth, we need to look not at starlight, but at a faint, cold glow that fills the entire sky. This is the cosmic microwave background, the afterglow of the Big Bang itself. To study its subtle imperfections, the European Space Agency launched the Planck satellite. Planck's exquisitely sensitive instruments mapped this primordial light in unprecedented detail, revealing tiny temperature variations, anisotropies, that are the blueprints for all future structure. These minute-hot and cold spots are imprints of quantum fluctuations stretched to cosmic size by inflation, the seeds from which galaxies like our own Milky Way would eventually grow. Planck's data gave us the most precise measurements of the universe's age, composition, and geometry, confirming its flatness and constraining the theories of what its earliest moments must have been like. Yet, even these powerful tools hit a fundamental wall. They can show us the ancient surface of last scattering, the shell of the cosmic microwave background, but they cannot see what, if anything, lies behind it. To probe the vast expanses closer to our observable limit, scientists use clever cosmic rulers and standard candles. One such ruler is etched into the very fabric of the cosmos, a fossilized sound wave from the primordial plasma. In the first few 100,000 years, the universe was a hot, dense soup of particles and light. Pressure waves like sound rippled through this soup. When the universe cooled and became transparent, these waves froze in place, leaving a preferred scale imprinted on the distribution of matter. Today, we see this scale as a subtle statistical tendency for galaxies to be separated by about 500 million light-years. By measuring this Barrian acoustic oscillation at different cosmic epochs, we can trace how the expansion of the universe has changed over time, a direct probe of the influence of dark energy. Another crucial tool comes from the catastrophic explosions of dying stars. A specific type of supernova, known as a type Ia, occurs when a white dwarf star accretes too much matter from a companion. These explosions have a remarkably consistent peak brightness, making them perfect standard candles. By measuring how dim they appear from vast distances, astronomers can calculate exactly how far away they are. It was the observation of these distant supernovae in the late 1990s that revealed they were fainter, and thus farther than expected, providing the shocking evidence that the expansion of the universe is accelerating, driven by dark energy. Each of these methods allows us to infer the properties and contents of the universe right up to the edge of our vision. We chart the large-scale structure, measure the expansion history, and test our cosmological models against the faint light of the horizon. But they are all fundamentally methods of looking back. They cannot show us what exists in the contemporary universe beyond that boundary. This creates a fascinating reliance on indirect evidence and theoretical extrapolation. We must use the physics we understand within our observable bubble to build models of what might lie outside it, models of inflation, the multiverse, or cosmic topology. The horizon is the ultimate laboratory wall, and we are left to deduce what might be on the other side by the echoes that reach us. This limitation, however, fuels an incredible engine of ingenuity. The next generation of observatories is already pushing forward. The James Webb Space Telescope, with its giant gold-plated mirror and infrared vision, is designed to see the very first galaxies to ever form, objects so distant and redshifted that their light has been stretched into the infrared part of the spectrum. Webb will look back to an era just after the cosmic dark ages, potentially revealing how those initial seeds from the cosmic microwave background grew into the structures we see today. Future missions will take even more precise measurements of the cosmic microwave background, searching for the faint, swirling patterns of gravitational waves from inflation, or the telltale matched circles that would indicate a wrapped, finite cosmos. Each new instrument brings the horizon into sharper and sharper focus, defining its properties with ever greater clarity. While we may never receive a photon from beyond it, we are learning to read the story of our cosmic home in exquisite detail, a story whose final chapters, for now, remain written in the dark. These powerful tools all rely on a common foundation, a framework of ideas that allows us to interpret the light and even speculate about the darkness. At the heart of our modern cosmic understanding lies Albert Einstein's theory of general relativity, published in 1915. This was a revolution in thought. Einstein proposed that gravity is not a force pulling objects together, but the result of mass and energy curving the very fabric of spacetime itself. Picture a heavy bowling ball placed on a trampoline, creating a deep well. A marble rolled nearby will spiral inward, not because of a direct pull, but because it is following the curved surface. Planets orbit stars and light itself bends because they are traveling along the contours of warped spacetime. General relativity gave us the equations to describe an entire universe that could be dynamic, that could expand or contract. It is this theory that first allowed us to mathematically conceive of a cosmos with a beginning, a Big Bang, and to understand the particle horizon as a fundamental feature of a finite-aged universe in motion. Yet, for all its power, general relativity is a theory of the very large, the cosmic scale. To understand the universe's first moments, where all matter and energy were compressed into a space smaller than an atom, we need a theory of the very small, quantum mechanics. This is the great divide in modern physics. Quantum mechanics describes the bizarre, probabilistic world of particles with stunning accuracy, but it does not include gravity. For decades, physicists have sought a theory of quantum gravity, a single framework that can marry the cosmic and the subatomic. One of the most promising bridges is the theory of cosmic inflation. Inflation uses the language of quantum field theory, which combines quantum mechanics with special relativity, to describe a hypothetical field that permeated the early universe. A tiny, random quantum fluctuation in this field could have triggered a phase of exponential, faster-than-light expansion, smoothing and flattening the cosmos in an instant. Inflation is not just an add-on to the Big Bang, it is the mechanism that sets the initial conditions for it. Crucially, as we explored earlier, some models of inflation are eternal, naturally giving rise to a multiverse of bubble universes. This is where speculation truly leaps forward, guided by another ambitious framework, string theory. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops or strands of energy. The different vibrations of these strings correspond to different particles, like notes on a violin string. To make the mathematics of string theory work consistently, it requires more than the 3 spatial dimensions we experience. It suggests there are 6 or 7 extra dimensions, curled up at every point in space at a scale far too small for us to perceive. This leads to an astonishing possibility that our entire 3-dimensional universe could be a membrane or brain floating within a higher dimensional space. Other brains could exist parallel to ours, potentially hosting other entire universes. An extension called M-theory, which unites different versions of string theory, paints a picture of an 11-dimensional multiverse where brains collide, creating big bangs or drift apart, forming separate cosmic domains. Each of these theoretical frameworks offers a different lens on what lies beyond. General relativity gives us the geometry of spacetime and the horizon itself. Inflation provides a mechanism for generating multiple, potentially infinite, cosmic domains from a quantum seed. String theory and M-theory supply the architecture for a higher dimensional reality where our universe is just one slice of a much grander structure. They predict not just more galaxies, but entirely different physical laws in other bubbles or on other brains, a landscape of possible universes. While these ideas remain theoretical and are not yet unified into a single, testable theory of everything, they are far from mere science fiction. They represent the furthest reaches of our current mathematical and conceptual tools, the rigorous stretching of logic and imagination to its absolute limit. They provide the scientific vocabulary for our deepest cosmic questions, transforming wonder into a form of exploration that happens not with telescopes, but with equations on a page. That baby picture of the universe is not a metaphor, but a literal physical reality we can measure. The cosmic microwave background radiation is the oldest light in existence, a fossilized glow that has been traveling for over 13 billion years. It is the afterglow of the moment the universe cooled enough for atoms to form, when the hot, opaque plasma of particles and light finally cleared, allowing photons to stream freely across space. This happened when the cosmos was a mere 380,000 years old, an infant compared to its current age. What we detect today is that same light, stretched and cooled by the expansion of the universe into the microwave part of the spectrum, bathing the entire sky in a faint, uniform chill. As cosmologist George Smoot famously described it, looking at the CMB is like seeing the face of creation itself. But this baby picture is not a smooth, featureless portrait. With instruments of exquisite sensitivity like the Planck satellite, we have mapped its minute imperfections. The sky is painted with tiny temperature fluctuations, hot and cold spots that differ by only a few millionths of a degree. These are not random blemishes, they are the cosmic seeds, the imprints of quantum fluctuations from the inflationary epoch, stretched to astronomical size. These minute ripples in density are the gravitational blueprints for everything that came after. The slightly denser regions would, over billions of years, pull in more matter through gravity, eventually growing into the galaxies, clusters, and vast filaments of the cosmic web we see today. By studying the statistical patterns of these hot and cold spots, scientists can read the universe's vital signs. The size and distribution of the fluctuations tell us the geometry of space is remarkably flat. They reveal the precise recipe of the cosmos: about 5% ordinary matter, 27% dark matter, and 68% dark energy. They even provide a timestamp confirming the universe's age of approximately 13.8 billion years. Beyond temperature, the light of the CMB carries another layer of information in its polarization, the direction its electric field vibrates. This polarization is a fingerprint of the universe's last interaction with matter, and it holds clues about the earliest moments, potentially even about gravitational waves generated during inflation. Yet, for all it reveals, this ancient snapshot also presents profound puzzles. Certain large-scale anomalies in the data defy simple expectations. One is the so-called cold spot, a region of the sky significantly cooler than our models predict. While it could be a statistical fluke or a foreground effect, some theorists have proposed more exotic explanations. Could it be the imprint of a collision with another bubble universe during inflation, a bruise on our cosmos from a contact with another realm? Another anomaly is an unexpected alignment of patterns on the largest scales, a possible preferred direction that seems to challenge the assumption of perfect uniformity. Could these hints be whispers from beyond our observable horizon, subtle influences from structures or forces so vast they curve the fabric of our local spacetime? The scientific community remains cautious, with most researchers favoring more conventional, if less thrilling, explanations within our standard models. But the mere possibility is tantalizing. It suggests that the CMB, our deepest view of the past, might also be a murky window to the greater beyond. It captures our observable domain in its infancy, but the conditions that shaped those initial ripples may have been influenced by a landscape far larger than our bubble. Studying this primordial light allows us to reconstruct our past with incredible precision, yet it simultaneously underscores a fundamental limit. We are analyzing a single, frozen frame from a film reel whose beginning we can only theorize about and whose later scenes, playing out in the contemporary universe beyond our horizon, we can never directly watch. The CMB is both our most powerful map and our most poignant reminder of the cosmic veil. The faint whispers of the cosmic microwave background are just the beginning of our conversation with the cosmos. A new generation of cosmic cartographers is preparing to launch, instruments of such staggering sensitivity they promise to redefine the map of our observable universe. The Vera C. Rubin Observatory, currently under construction in Chile, will not look at a single point in the sky, but will capture the entire southern hemisphere in exquisite detail, night after night for a decade. Its mission is a monumental time-lapse film of the cosmos, detecting billions of galaxies and tracking the subtle dance of their motions. This immense survey, called the Legacy Survey of Space and Time, will create the most precise three-dimensional map of the large-scale structure ever made. By charting how cosmic structures grow and how their distribution changes across billions of years, it will put dark energy under a microscope, testing whether its repulsive force has remained constant or changed over the lifetime of the universe. Joining this effort from space is the European Space Agency's Euclid satellite. Euclid's specialty is a phenomenon called weak gravitational lensing. As light from distant galaxies travels toward us, the gravity of invisible dark matter clumps warps its path, slightly distorting the shapes of millions of galaxies. By meticulously measuring these tiny distortions, Euclid will trace the invisible skeleton of dark matter that underpins the cosmic web. This map will be another crucial test for dark energy, as the growth of this dark matter web is directly stifled by the accelerating expansion of space. Together, Rubin and Euclid will subject our leading cosmological models to a stress test of unprecedented scale. On an even grander stage, the Square Kilometre Array, or SKA, is taking shape across continents in South Africa and Australia. This is not a single telescope, but a vast network of radio antennas that will function as one colossal ear, listening to the universe in radio waves. It will detect the faint hydrogen gas from the cosmic dawn, tracing the formation of the very first stars and galaxies. It will also use pulsars, the ultra-precise cosmic lighthouses, as a galaxy-scale gravitational wave detector. By monitoring the rhythmic ticks from an array of pulsars across the Milky Way, the SKA could detect the low-frequency hum of gravitational waves from supermassive black hole mergers, or even the faint, primordial rumble from cosmic inflation itself. Finding that primordial signal would be a direct peek into the universe's first trillionth of a second, offering empirical evidence for the mechanism that may have spawned our entire cosmic bubble. While none of these missions can see a single photon from beyond our particle horizon, they can search for its ghostly imprint. They will test for the subtle signatures of a finite, wrapped cosmos, looking for the telltale matched circles or strange correlations in the data that could indicate our universe is connected in a non-trivial way. They will scour the data for anomalies, for statistical oddities in the distribution of galaxies, or the cosmic microwave background that cannot be explained by our standard models. Such an anomaly could be the most exciting result of all, a potential clue that something vast and unfamiliar, a neighboring bubble universe, a gravitational pull from an unseen superstructure, or a domain with different physics, is exerting an influence on our local neighborhood. The future windows may not rely on light alone. Neutrino astronomy, which detects these nearly massless, ghostly particles that stream through matter unimpeded, could one day provide a snapshot of the universe even earlier than the cosmic microwave background, from a time when it was still opaque to light. Similarly, next-generation gravitational wave observatories in space could listen to the chorus of mergers from the earliest black holes, painting a dynamical picture of the universe's first structures. Each new window refines our picture of the cosmos within our horizon, tightening the constraints on our theories. And by rigorously defining what our observable universe is, we more sharply delineate what it is not, bringing the question of what lies beyond from pure philosophy into the realm of constrained scientific speculation. The answers are not written yet, but the tools to write them are being forged. There is a final, humbling frontier we must acknowledge, one that exists not in space, but in the nature of knowledge itself. The most profound mystery of what lies beyond our cosmic horizon may be that we can never truly know it. This is the epistemic boundary, the limit of what science can ever tell us. Our most powerful tools are bound by the laws of physics they seek to explain. We cannot receive a signal, a particle, or a photon from a region that is causally disconnected from us, receding faster than light itself. Any theory about those realms, no matter how elegant or compelling, faces a monumental challenge. It may be forever untestable. The philosopher of science Karl Popper placed a crucial criterion at the heart of the scientific method: falsifiability. A true scientific theory must make predictions that could, in principle, be proven wrong by observation or experiment. This is what separates science from pure speculation. Yet, when we speak of an infinite multiverse, of other bubble universes with different physical laws, or of cosmic cycles before our Big Bang, we are often venturing into territory that seems to resist this very test. How could we ever falsify the existence of a universe we can never interact with? This pushes some of our grandest cosmological ideas to the very edge of science, bordering on metaphysics. This is not to say such ideas are worthless, far from it. They are often the necessary extensions of our most successful theories, like inflation or string theory, showing us where the mathematics naturally leads. They expand our imagination and challenge our assumptions, serving as crucial thought experiments that shape future questions. But we must hold them with a certain intellectual humility, recognizing the clear line between a testable prediction and a beautiful, yet currently untestable story. This limitation extends beyond our instruments, touching the nature of human cognition. Our brains evolved to navigate a world of medium-sized objects moving at modest speeds. We instinctively think in terms of cause and effect, of a past and a future, and of a three-dimensional space. Concepts like a universe with 10 spatial dimensions, a reality where time is emergent and not fundamental, or a cosmos that is truly infinite, strain our neural wiring to its breaking point. We can write the equations, but we cannot truly picture the reality. So where does this leave our quest? It encourages a dual mindset, one of boundless curiosity, driving us to build better telescopes and devise more precise experiments to map every inch of our observable universe. And another of sober critical thinking, asking sharp questions about what constitutes evidence and what remains, for now, a compelling narrative. This uncertainty is not a failure of science. It is a defining feature of our encounter with the ultimate scales of reality. The cosmic horizon, therefore, stands as a permanent symbol. It represents both the incredible power of the human intellect to reconstruct 13.8 billion years of cosmic history and the ultimate limit of that power. Some mysteries may remain forever shrouded, not by a lack of effort, but by the fundamental architecture of the cosmos itself. Yet, in a beautiful twist, this very limitation is what keeps the flame of wonder alive. It transforms the universe from a puzzle to be solved into a story to be continually explored, reminding us that the journey of questioning is often more meaningful than any final answer we might hope to find. Long before telescopes mapped the cosmic microwave background, artists and storytellers were already sketching the edge of everything. When science reaches its observational limits, human imagination takes over, translating the cold equations of cosmology into stories that resonate with awe, dread, and wonder. The unknown beyond our horizon has always been a canvas for our deepest hopes and fears. In the early 20th century, writer H.P. Lovecraft crafted tales where the mere glimpse of this cosmic outside shattered human sanity. His fictional pantheon of ancient, indifferent gods existed in the spaces between stars and beyond the geometry of known space. Lovecraft's horror was not about monsters in the dark, but about the terrifying insignificance of humanity in a vast, uncaring multiverse. His work gave narrative form to the existential dread that can accompany cosmological discovery, a fear that what lies beyond is not just unknown, but actively hostile to our understanding. This artistic tradition of cosmic horror reflects a very real human anxiety about the scale of reality, giving it a face, however alien, and a story we can feel. A generation later, cinema offered a radically different yet equally profound interpretation. Stanley Kubrick's film 2001, A Space Odyssey, presented the beyond not as a source of horror, but of transcendent, mysterious evolution. The iconic monolith is an artifact of an unfathomably advanced intelligence, a silent teacher placed at celestial waypoints to guide humanity's next leap. The film's final, psychedelic journey beyond the limits of human space is a visual poem about transformation. It suggests that what lies at the cosmic edge might not be more stars, but a gateway to a new state of being, emerging with a higher plane of intelligence or existence. Where Lovecraft saw madness, Kubrick saw metamorphosis. Both, however, agree on one central point: the encounter with the ultimate frontier changes the traveler irrevocably. These artistic visions serve a crucial cultural function. They process the raw data of scientific possibility, infinite space, alien physics, higher dimensions, and filter it through human emotion. They ask not what is there, but what it would mean to find it. This creative exploration extends far beyond horror and science fiction. Modern films like Contact, based on Carl Sagan's novel, grapple with the spiritual and philosophical implications of first contact with an intelligence from the cosmic deep. The protagonist's journey through a wormhole is less about the engineering of the tunnel and more about the ineffable, emotional experience of connection with a vast, ancient cosmic design. Video games, too, have become a powerful medium for this exploration. Titles like the video game series Elite, Dangerous, or No Man's Sky offer players a simulated, procedural universe to explore, embodying the human desire to go farther, to see what's over the next digital hill. They provide an interactive metaphor for the endless frontier, satisfying a primal urge to map the unmappable, even within a constructed reality. Each of these works, in its own way, creates a cultural metaphor for the scientific unknown. They translate the acceleration of dark energy into a narrative of pursuit or isolation. They mold the multiverse hypothesis into tales of alternate selves and branching destinies. They give the cold void a temperature, a sound, and an emotional weight. This fusion of art and science is not a distraction from truth, but a vital partner in its pursuit. The artist asks the questions the scientist must later formulate, and the scientist discovers the realities that inspire the artist's next vision. They are two languages describing the same profound mystery. Art provides the metaphors that help us grasp concepts our logical minds struggle to hold, making the inhuman scale of cosmology feel personal and visceral. It reminds us that our quest to understand the cosmos is driven by more than curiosity. It is driven by a need to find meaning, beauty, and perhaps even a sense of home within the overwhelming vastness. While a telescope measures the redshift of a galaxy, a painting or a film can measure the tremor it causes in the human soul. Together, they form a more complete picture of our relationship with the edge of all things, acknowledging that the journey outward is always inevitably a journey inward. That artistic search for meaning finds a strange echo in a scientific principle that turns our gaze inward. Our very presence here, asking these questions, might be the most important clue about the nature of the cosmos itself. This is the Anthropic principle, a simple yet profound idea that forces us to consider our place in the grand scheme. In its most basic form, it states that the universe we observe must be compatible with the existence of conscious observers like us. We should not be surprised to find ourselves in a universe with the right conditions for life, because if it were any different, we would not be here to notice. This principle, introduced by physicist Brandon Carter in the 1970s, began as a logical tautology but soon blossomed into one of cosmology's most heated debates. It arises from a startling observation: the fundamental constants of our universe appear exquisitely fine-tuned. Consider the strength of gravity or the precise mass of an electron. If these values were altered by even a tiny fraction, the consequences would be cosmic. Stars might never form, atoms would be unstable, and the complex chemistry necessary for life would be impossible. The universe would be a dark, empty void or a chaotic soup of particles that instantly collapsed. The odds of all these constants aligning just right seem astronomically small, as if the cosmos were designed with life in mind. This fine-tuning presents a powerful mystery. The Anthropic principle offers two main interpretations to explain it, known as the weak and strong forms. The weak Anthropic principle is the more conservative stance. It simply notes that we must find ourselves in a region of the universe and at a time in its history where conditions allow for observers. It does not require multiple universes, just the acknowledgement that our viewpoint is not random. We are carbon-based life forms who need liquid water, so we naturally find ourselves on a planet with water, orbiting a stable star in a galaxy old enough to have forged the necessary heavy elements. This principle acts as a selection effect on our observations. The strong Anthropic principle takes a much more radical step. It suggests that the universe must have properties that allow life to develop at some stage in its history. This version often leans into teleology, the idea that the universe has a purpose or goal, which many scientists find philosophically troubling as it lies outside the realm of testable science. However, the most scientifically compelling outgrowth of this thinking is the multiverse interpretation. In this view, the strong Anthropic principle finds its home. If a vast multiverse exists, containing countless domains or bubbles with different physical constants, then it is no wonder we find ourselves in one of the rare habitable ones. We could not exist in the others. Our cosmic address is not special because the whole universe is designed for us, but because we are a product of a rare, life-permitting corner of a much larger and mostly inhospitable reality. This framework transforms the question of what lies beyond our horizon. If the multiverse is real, then beyond our particle horizon, we might not find more galaxies like our own. We might instead find the border of our hospitable bubble, adjacent to a domain where gravity is too strong and stars burn out in seconds, or where the nuclear forces are too weak and matter cannot coalesce. The greater cosmos could be a patchwork of physical laws, a cosmic archipelago where islands of stability like ours are separated by vast seas of sterile, alien physics. This perspective does not necessarily imply design, but rather a form of cosmic natural selection. In an ensemble of universes, some will, by pure chance, have the right numbers. We live in one of those lucky draws. The debate between a single, uniquely tuned universe and a multiverse of possibilities remains unresolved. It touches on the deepest questions of existence, blurring the line between physics and philosophy. The anthropic principle, in all its forms, serves as a crucial bridge. It links the intimate, local conditions that allowed life to emerge on Earth directly to the largest-scale structures of reality, whether that is a single infinite universe or a frothing multiverse. It suggests that our ability to look up and wonder about the edge of everything is not an accident, but a direct consequence of the kind of cosmic neighborhood we inhabit. Our observable universe might be a rare oasis, a garden in a desert of unimaginable scale, and the horizon is the wall that keeps the desert's harsh winds at bay, allowing our story to unfold within. But what is this vacuum energy, this generative nothingness, really made of? To understand it, we must shrink our perspective from the cosmic scale down to the quantum realm. Even in what we call empty space at the tiniest scales, the universe is never truly still or silent. According to quantum field theory, every point in space is a simmering sea of potential, a foam of fleeting energy. This is the quantum vacuum, and it is far from empty. Pairs of virtual particles and their antiparticles constantly wink into existence, borrowing energy from the vacuum for an unimaginably brief moment before annihilating each other and returning the energy. This ceaseless activity, these quantum fluctuations, give the vacuum a baseline energy, a hum of existence that permeates every cubic centimeter of the cosmos. It is a dynamic, seething substrate, the true ground state of reality. Physicist Lawrence Krauss has explored this idea in depth, framing it as a universe from nothing. But his nothing is not a philosophical void. It is this unstable quantum vacuum, a something with specific, measurable properties governed by the laws of physics. In this view, the question of what existed before the Big Bang transforms. Perhaps there was no before in a temporal sense, but rather a pre-existing metastable quantum vacuum, a state of restless potential. A random, large enough quantum fluctuation in this vacuum could have tunneled through an energy barrier, triggering the inflationary expansion that became our universe. Our entire cosmos, with all its galaxies and stars, could be the product of a single, monumental quantum burp in an eternal, featureless sea of potential. This concept stretches our intuition to its limit. It suggests that beyond our observable horizon, in the vast expanses where inflation may still be raging, this primordial quantum foam is the dominant reality. There, the vacuum energy is not a subtle background hum, but an overwhelming creative force. It is a generative nothingness, continuously spawning new bubble universes through quantum tunneling, each with its own random set of physical constants and laws. What we perceive as the solid, stable universe of galaxies is just one calm eddy in a turbulent, infinite ocean of quantum possibility. the line between existence and non-existence blurs into meaninglessness. The vacuum is not a container for things, it is the thing itself, constantly giving birth to reality and taking it back. This vision of what lies beyond is perhaps the most radical of all. We are not looking out toward more stars or other cosmic bubbles, but toward the very fabric from which all such structures are momentarily woven. The horizon becomes the edge of our local crystallization, beyond which lies the raw, unformed potential of the quantum field, eternally dreaming new worlds into being. The quantum vacuum's restless potential finds its ultimate expression in one of the universe's most enigmatic objects. A black hole is not just a cosmic vacuum cleaner, it is a laboratory for the most extreme physics, a place where our understanding of reality is pushed to the breaking point. At its boundary, the event horizon, gravity becomes so intense that not even light can escape. According to classical physics, anything that crosses this threshold is lost forever. Its information, the specific arrangement of particles that made it unique, seemingly erased from our universe. This creates a direct conflict with quantum mechanics, which holds that information can never be truly destroyed. This standoff is known as the black hole information paradox, and its resolution may rewrite the laws of physics. The late physicist Stephen Hawking made this paradox famous. He showed that black holes are not completely black, they slowly evaporate by emitting a faint glow of particles now called Hawking radiation. This radiation appears to be purely thermal, carrying no information about what fell in. If a black hole evaporates completely, all the information about the stars, planets, or spaceships it consumed would vanish, violating a core quantum principle. This paradox forced physicists to a startling realization. The event horizon is not a simple one-way door. It may be a transformative surface where information is not lost, but radically scrambled and preserved in a way we do not yet understand. This line of thinking led to the holographic principle, the idea that all the information describing a volume of space can be encoded on its two-dimensional boundary. A black hole's information might be stored on its event horizon like data on a cosmic hard drive, with the three-dimensional interior being a projection of that data. This profound link between information, gravity, and quantum mechanics reshapes our view of the cosmos itself. It invites a breathtakingly speculative question: what if our entire universe is the interior of a black hole in a larger parent universe? This concept, known as black hole cosmology, suggests a staggering vision of cosmic nesting. In this model, the Big Bang was not a singular beginning from nothing, but the violent birth of a new spacetime region within an existing one. The immense gravitational collapse of a massive star in some other universe could have forged our cosmos in its fiery crucible. Our expanding universe, with its cosmic microwave background, might be the analog of the Hawking radiation emitted by that parent black hole. The edge of our observable universe, the particle horizon, would then correspond not to an edge of all existence, but to the interior wall of this cosmic containment. Beyond that horizon, we would not find more galaxies like our own. We would find the interior geometry of the black hole that contains us, or perhaps, if we could somehow pass through, the exterior landscape of the parent universe from which we originated. This idea implies a hierarchical, fractal structure of realities. Each universe could contain black holes that are themselves new universes, birthing endless chains of cosmic ancestry. Our laws of physics would then be a local set of rules, determined by the specific conditions of our black hole's formation. Other universes, born from different collapses, could have entirely different constants and forces. This speculative framework does something remarkable. It directly connects the physics of the infinitely small, the quantum gravity needed to describe a black hole's core, with the physics of the infinitely large, the cosmology of our entire expanding cosmos. It suggests that the key to understanding what lies beyond our horizon may not be a bigger telescope, but a deeper theory of how information, space, and time are fundamentally woven together. While this remains a highly theoretical idea with no direct evidence, it offers a startling and elegant vision. The ultimate frontier might not be a distant place in space, but a different layer of reality altogether, a nested existence where every horizon is both an end and a beginning. These grand cosmic structures, from black holes to multiverses, are all described by mathematics and physics, but they are perceived by something far more intimate, the conscious mind. This leads us to a mystery that sits at the very heart of our quest to understand reality. What if the act of observation itself is not a passive recording of the universe, but an active participant in its unfolding? This question emerges from the bizarre world of quantum mechanics, where particles exist in a haze of probability, a superposition of many possible states until they are measured. In some interpretations of quantum theory, the act of observation by a conscious entity is what forces this cloud of possibilities to collapse into a single, definite outcome. This is the famous observer effect, and it suggests a profound, unsettling link between the mind and the cosmos it seeks to understand. It implies that at the most fundamental level, the universe may not have a definite form until it is perceived. This idea, championed by figures like physicist John Wheeler, transforms the cosmos from a pre-existing machine into a kind of participatory reality, a cosmic story that requires a reader to give it final shape. If this is true even in a limited quantum sense, it forces a philosophical earthquake. Does the universe exist independently in a definite state, waiting for us to discover it, or does our consciousness play some role in bringing it into being? This is not merely abstract philosophy, it is a frontier where science meets the hard problem of consciousness, the mystery of why and how subjective experience arises from physical processes in the brain. If consciousness is somehow fundamental to the fabric of reality, not just an accidental byproduct of complex brains, then our entire cosmic perspective shifts. Consider the vast expanse beyond our observable horizon. We have explored theories of infinite space, multiverses, and wrapped geometries, all assuming an objective reality that exists whether we look or not. But what if the nature of that beyond is not fixed? Could there be regions of the cosmos where different forms of consciousness, or different rules of observation, perceive entirely alternate realities? In a multiverse of infinite possibilities, there might be domains where the local laws of physics are not just different, but are inextricably linked to the kind of mind that observes them. A being with a radically different sensory apparatus or cognitive structure might not perceive galaxies and stars at all, but an entirely other organization of reality from the same underlying quantum fields. This is, of course, highly speculative, venturing far beyond current empirical science, yet it touches on a deep and ancient human intuition that the world we see is shaped by the tools we use to see it, both our telescopes and our own minds. It adds a layer of profound subjectivity to our cosmic quest. We are not just mapmakers of an external territory, we are also the architects of our own experience of that territory. The edge of the observable universe then becomes more than a limit of light. It becomes the boundary of a reality co-created by the cosmos and our own consciousness. Exploring this mystery does not provide easy answers, but it enriches the questions. It bridges the cold equations of cosmology with the warm, inexplicable fact of our own awareness. It asks us to consider that the greatest frontier may not be out there in the dark, but in here, in the nature of perception itself. The final answer to what lies beyond may depend, in some small but fundamental way, on who is asking. Our contemplation of the cosmos is not a neutral act. It carries weight, a profound responsibility that grows with every new discovery and every technological leap. As we stand on the threshold of potentially contacting other intelligences or manipulating the fabric of spacetime itself, we must ask not only what we can do, but what we should do. The ethical dimensions of cosmic exploration are as vast as the universe we seek to understand. Consider the momentous possibility of detecting a signal from an extraterrestrial civilization. Such a discovery would irrevocably change our view of our place in the universe, uniting humanity in a shared moment of awe. Yet it also presents immense ethical questions. How should we respond? Who speaks for Earth? A hastily crafted reply born of fear or arrogance could have consequences spanning generations. The protocols established by organizations like the International Academy of Astronautics emphasize caution, consultation, and a commitment to peaceful communication, recognizing that our first interstellar conversation must be guided by wisdom and a deep sense of planetary responsibility. This extends to our own robotic emissaries. The principle of planetary protection is a direct ethical application of cosmic stewardship. When we send probes to other worlds, like Mars or the icy moons of Jupiter, we go to extraordinary lengths to sterilize them, ensuring we do not contaminate pristine environments with earthly microbes. This is not just about preserving the scientific integrity of our search for alien life. It is an act of respect. We acknowledge that these other worlds have their own stories, their own potential for life, and we have a duty to explore without carelessly imposing our own biological narrative upon them. The same foresight applies to the potential use of resources beyond our planet. The asteroids and moons of our solar system contain vast quantities of water, metals, and rare minerals. Their responsible use could enable a sustainable future for humanity in space, powering further exploration. But an unregulated rush to claim and exploit these celestial bodies risks repeating the cycles of conflict and environmental harm we have seen on Earth. The emerging framework of space law grapples with these questions, seeking to frame such activities not as a free-for-all, but as endeavors that benefit all humankind. Perhaps the most profound ethical guide comes from the late astronomer Carl Sagan. He consistently advocated for a posture of cosmic humility. The famous pale blue dot image, a photograph of Earth taken from the edge of our solar system by the Voyager 1 probe, was a visual sermon on this theme. Our world appears as a tiny, fragile speck of light suspended in a sunbeam. All of human history, every triumph and every conflict, has occurred on that barely visible pixel. Sagan urged us to view this image as a reminder of our shared fate and our common responsibility to care for that pale blue dot and for each other. This humility must scale with our ambition. If future technologies, born from theories of quantum gravity or advanced propulsion, ever allow us to probe the regions beyond our cosmic horizon or manipulate spacetime on large scales, the ethical stakes become almost unimaginable. Could such an experiment inadvertently affect distant regions of the cosmos, or even other cosmic bubbles in a multiverse? While this sounds like science fiction, the ethical principle is timeless. Our power to affect the universe must be matched by a profound reverence for it. This means viewing the cosmos not as a collection of resources to be consumed or puzzles to be solved, but as a shared heritage. The grand structures, the ancient light, the very laws of physics, constitute a story that belongs to no one civilization, but to existence itself. Our role is that of careful students and gentle custodians. As we push the boundaries of knowledge, we must balance our boundless curiosity with ethical foresight, ensuring that our journey into the great beyond is conducted not with a conqueror's arrogance, but with an explorer's respect for the sacred, silent depths of the unknown. This profound responsibility to the cosmos finds a deep echo in humanity's oldest questions. Long before telescopes charted the cosmic microwave background, every culture looked to the stars and asked not just what was out there, but why it was there at all. The mystery of what lies beyond the physical universe is a bridge between two great human endeavors, theology and cosmology. For millennia, spiritual traditions have described realms that transcend our material world, from heavenly abodes and afterlife planes to the very dwelling place of a divine creator. These concepts address the ultimate beyond not as a physical location, but as a dimension of meaning, purpose, and sacred reality. In many faiths, the physical cosmos is seen as a creation, a finite expression of an infinite source. The edge of the universe, in this view, is not a wall of ancient light, but a boundary between the temporal and the eternal, the created and the uncreated. This theological perspective offers a different kind of map, one charted not by redshift but by revelation and contemplation, seeking to understand the origin and destiny of existence itself. Interestingly, some of the most cutting-edge ideas in modern cosmology find curious parallels in ancient spiritual thought. The concept of a multiverse, with its infinite array of bubble universes, resonates with certain Hindu and Buddhist cosmologies that speak of countless world systems, each with its own cycle of creation and dissolution. The cyclic universe model, where cosmos follows cosmos in an endless rhythm, mirrors ideas of eternal return found in Stoic philosophy and some indigenous creation stories. These parallels are not evidence that ancient prophets had telescopes, but rather a testament to the power of the human imagination when confronted with the vast unknown. Both science and spirituality are attempts to read the same profound mystery, though with different languages and methods. Today, this intersection is the subject of serious and respectful dialogue. Institutions like the Vatican Observatory, staffed by Jesuit scientists, actively research astrophysics and cosmology. Their work embodies a search for harmony, exploring how a universe governed by physical laws can also be seen as a coherent creation. Prominent scientists, from the devout to the atheist, engage with theologians on questions of fine-tuning, the origin of the laws of physics, and whether a multiverse nullifies or complements the idea of a creator. The physicist and Anglican priest John Polkinghorne framed this not as a conflict but a conversation. He argued that theology asks why questions, seeking ultimate meaning, while science asks how questions, uncovering mechanisms. They are complementary lines of inquiry into the same rich reality. This ongoing dialogue does not seek to prove or disprove faith with a telescope, nor to sanctify science with scripture. Instead, it acknowledges that at the very edge of knowledge, where our data runs out and our theories become untestable, we enter a space where worldview, philosophy, and yes, spirituality inevitably shape our interpretation. The question of what lies beyond our cosmic horizon is ultimately a question about the nature of reality itself. Is it solely a self-contained physical system, however vast, or is it embedded within a larger context of meaning or consciousness that science, by its very methodological limits, cannot measure? Exploring this intersection highlights the full spectrum of the human response to the cosmos. It shows that our drive to understand the beyond is not merely technical, but deeply existential. We are creatures who build particle accelerators and write psalms, who map dark matter and contemplate the divine. Both impulses spring from a sense of wonder and a need to find our place in the grand scheme. In the end, whether one sees the ultimate frontier as a quantum vacuum, a multiverse, a heavenly realm, or an ineffable mystery, the shared human act is looking up and asking. This diversity of interpretation is not a weakness but a richness. It reminds us that the cosmos is so vast, so profound, that it demands every tool of understanding we possess, from mathematics to meditation, to even begin to grasp its story. The universe might be written in a language far more fundamental than mathematics. It could be written in code. This is the simulation hypothesis, a modern philosophical proposition that reframes our entire cosmic mystery in digital terms. What if our universe, with its galaxies, its laws of physics, and even our own conscious experience, is not a base reality, but an artificial construct? A simulation running on some unimaginably powerful computer, built by a civilization far more advanced than our own. Philosopher Nick Bostrom formalized this startling idea, arguing from a simple logical chain. If any civilization reaches a post-human stage capable of creating vast, detailed simulations of conscious beings, and if they have any interest in running such simulations, then the number of simulated minds would vastly outnumber the biological ones. Statistically, we are more likely to be one of those simulated minds than an original biological being. In this view, the edge of our observable universe is not a particle horizon born of an ancient Big Bang. It is a render limit, a boundary set by the computational resources allocated to our particular simulation instance. The cosmic microwave background is not an afterglow of creation, but the textured wallpaper of our digital container, the highest resolution texture the system can display at this scale. What, then, lies beyond that horizon? One possibility is simply more simulation, but of a lower resolution or less detailed nature, areas where the simulating computer conserves processing power for the regions where conscious observers are present. Another, more mind-bending possibility is that beyond our horizon lies the architecture of the simulation itself. The vast, dark voids between galactic filaments might not be empty, but could correspond to the underlying data structures or the blank canvas of the computational matrix. Our entire cosmos could be one of countless simulations running in parallel on some cosmic server farm, a single thread in a vast tapestry of virtual realities, each with its own slightly tweaked physical constants. This hypothesis draws its plausibility from observable trends. Our own technology is advancing rapidly toward virtual and augmented realities that feel increasingly immersive. Video games now simulate entire planets with realistic physics and ecosystems. If this trajectory continues for thousands or millions of years, a sufficiently advanced civilization could indeed create simulations indistinguishable from reality for the entities within them. From an information theory perspective, some physicists note that our universe operates in discrete, quantized units, much like the pixels on a screen or the bits in a computer. The finite speed of light could be seen as a processor speed limit, ensuring causality is maintained within the simulation. While this idea is currently untestable and firmly in the realm of philosophy, it forces a profound shift in perspective. It challenges the very assumption that our quest to understand the cosmos is a journey outward into a physical beyond. Instead, it might be a journey inward into the logic and source code of our own existence. If true, the ultimate frontier is not a place in space but a layer of abstraction. The creators of the simulation, whoever or whatever they are, would exist in a meta-reality, a base layer of existence that we, as entities within the program, could perhaps never directly access or comprehend. Our most fundamental laws of physics would be the algorithms of the simulation, and phenomena like quantum superposition could be artifacts of lazy evaluation, where the system only calculates definite states when an observation is made to save processing power. This digital reframing does not diminish the wonder of the cosmos, it transmutes it. It asks us to consider that the beauty of a spiral galaxy or the mystery of a black hole might be expressions of a sublime and elegant code. It places our search for meaning in a new context. Are we seeking the mind of a creator or the logic of a programmer? The simulation hypothesis, for all its speculative nature, serves as the ultimate mirror. It reflects our own technological aspirations and our deepest philosophical anxieties back at us, proving once again that the human drive to understand reality will use every tool available, from telescope lenses to the metaphor of the computer, to sketch a map of the unimaginable. There is a quiet music woven into the fabric of the cosmos, a harmony that speaks not in light or gravity, but in sheer elegance. The equations that describe our universe possess a startling beauty, a kind of mathematical poetry that feels as much like art as science. Consider the breathtaking simplicity of Einstein's field equations, where the curvature of spacetime on one side perfectly balances the matter and energy within it on the other. It is a single, concise line that describes everything from the orbit of a planet to the expansion of the entire cosmos. This is not an accident. For many of the greatest theoretical physicists, beauty has been a trusted compass, guiding them toward truth long before experiments could confirm it. Paul Dirac, who predicted the existence of antimatter from the sheer elegance of his mathematics, famously held that beautiful equations were more likely to be correct than ugly ones. He believed the universe at its core was fundamentally beautiful. This aesthetic sense extends from the abstract to the observable. Look at the spiral arms of a galaxy, a logarithmic curve echoing the shape of a nautilus shell. Examine the large-scale structure of the universe, where galaxies cluster into vast filaments and walls, a cosmic web that mirrors the branching of neurons in a brain or the veins of a leaf. These are patterns that repeat across nature, governed by the same underlying principles of gravity and dynamics. They suggest an inherent order, a preference for certain forms that are not just functional, but deeply pleasing to the human mind. This leads to a captivating thought about the great beyond. If our observable universe, with all its splendor, is governed by laws of such profound elegance, then what principles might govern the realms we cannot see? The cosmological order we have mapped, the symmetry, the patterns, the mathematical harmony, may be just a local melody within a far grander symphony. The laws that shape other cosmic bubbles in a multiverse, or that define the geometry of a higher dimensional bulk, could be expressions of an even more beautiful and unified mathematics. The pursuit of a theory of everything, a single framework uniting all forces, is driven in large part by this quest for ultimate elegance. Physicists seek a theory so natural, so inevitable in its structure, that its beauty is its own evidence. This transforms our perspective on the cosmic horizon. It is not merely a wall hiding more stuff, but a curtain veiling a deeper kind of truth. We are not just searching for more galaxies, but for more beautiful laws. This aesthetic dimension invites us to see cosmology as the highest form of art, a creative act of discovery where the universe is both the artist and the canvas. The spirals, the equations, the symmetries are all brushstrokes in a masterpiece whose full composition extends into the dark. So when we wonder what lies beyond the edge, we might also ask what beautiful, unseen mathematics is at work out there, waiting for a mind to one day appreciate its form. That mathematical beauty resonates on a deeply human level, touching something beyond logic, staring into the cosmic deep, into the possibility of an infinite beyond, does more than fill our minds with facts. It stirs our souls. This is the profound psychological impact of cosmic immensity, a feeling so potent it has a name, the overview effect. Astronauts who have seen Earth from orbit describe a sudden, overwhelming shift in awareness. The planet transforms from a map into a living, fragile home, suspended in a breathtaking void. National borders vanish, and a deep sense of global unity and responsibility takes hold. Contemplating the scale of the cosmos, the idea of realms forever beyond our sight, amplifies this feeling to an almost unimaginable degree. It can be a dizzying cocktail of awe and a piercing sense of our own smallness. We are temporary beings on a speck of dust orbiting an average star in a galaxy that is one of billions, inside a bubble of reality that may be just one among an infinity of others. In the face of that, our daily worries and conflicts can seem vanishingly small. Yet, psychologists are discovering that this feeling of awe is not a negative one. It does not lead to despair, but to something quite the opposite. Studies show that experiencing awe, whether from a mountain vista, a symphony, or an image from the James Webb Space Telescope, can reduce stress, increase feelings of connectedness, and promote overall well-being. It shrinks the ego and expands the sense of self to include something much larger. This cosmic perspective forces a kind of mental reset. The colleague who annoyed you, the traffic jam that frustrated you, the petty grievance you held onto, these things lose their sharp edges when held against the backdrop of 13.8 billion years and 46 billion light years. This is not about diminishing our personal stories, but about contextualizing them within the grandest story of all. The awe we feel is a form of cognitive expansion. It makes us more curious, more open to new ideas, and more likely to engage in prosocial behavior, to help others and feel part of a collective whole. When we grasp, even for a moment, that we are the universe itself becoming conscious, that the atoms in our bodies were forged in the hearts of long-dead stars, a profound connection replaces the feeling of isolation. We are not separate from the cosmos, we are a dynamic, thinking part of it. Exploring the great beyond, therefore, is far more than an intellectual exercise. It is an emotional and spiritual journey. It invites a healthy, grounding humility, the understanding that we are not the center of everything. But simultaneously, it offers an incredible inspiration, the realization that we are a rare way for the cosmos to know itself. This duality is a powerful source of perspective. It can motivate us to live with more kindness, to protect our pale blue dot, and to contribute to the ongoing human project of understanding. The next time you feel overwhelmed by the smallness of life, step outside on a clear night. Look up. Remember that you are standing at the edge of a mystery so vast it defies comprehension, and yet you are here, capable of wondering about it all. That act of wonder, that embrace of the awe, is perhaps the most human and the most cosmic thing you can do. It connects your brief, brilliant moment of consciousness directly to the silent, ancient dark beyond the edge of everything. These separate threads of mystery are not isolated. They weave together, each one pulling on the others to form a single, breathtaking tapestry of possibility. The chaotic inflationary landscape does not just explain our smooth, flat universe. It naturally gives rise to the multiverse, an endless foam of bubble realities. The quest to understand what happened before the Big Bang is the same quest for a theory of quantum gravity, a framework that might also resolve the paradox of a black hole's event horizon and suggest our universe is a holographic projection. The dark energy accelerating our expansion today may be the same vacuum energy that powered inflation in the first fleeting moments, a cosmic symmetry linking the beginning to the end. These are not competing stories but different chapters of the same grand narrative. The shape of space, the nature of time, the origin of structure, and the fate of all we see are intimately connected, each mystery a doorway into the next. This interconnectedness reveals a crucial truth. No single discipline holds the key. To even approach these questions, we must think in a way that transcends traditional boundaries. The astrophysicist mapping galaxies needs the particle physicist probing the subatomic realm. The mathematician exploring non-Euclidean geometries collaborates with the philosopher questioning the nature of reality and the limits of knowledge. The search for meaning in an infinite cosmos draws upon theology, while the drive to build the next great telescope is an feat of engineering. This is the essence of modern cosmology. It is a profoundly interdisciplinary endeavor, a collective human project to understand our place in the whole. This synthesis leads us away from a simple, linear story and toward a vision of the cosmos as a dynamic, creative, and perhaps even living system. It is not a static stage, but an unfolding process where spacetime itself can bend, branch, bubble, and rebound. The universe might be one of many in a multiverse, finite yet unbounded in a higher dimension, or a simulation in a vast digital archive. Each framework offers a different lens, a different set of metaphors for grappling with the ungraspable. Together, they form a spectrum of plausibility, from the well-tested to the highly speculative, all rooted in the logical extension of our current best theories. This tapestry of possibilities is not a sign of confusion, but of richness. It shows that our universe, in all its splendor, is likely just a single expression of a deeper, more fundamental reality whose full nature still eludes us. We are not closing in on one final answer, but expanding into a landscape of ever more profound questions. The journey to the edge has shown us that the ultimate frontier is not a place we will one day reach, but a horizon of understanding that forever recedes, inviting us to look further, think deeper, and wonder more boldly than ever before. Our journey to the edge of everything leaves us not with a final map, but with a deeper, more resonant kind of understanding. We have traveled through realms of theory, from the endless expanse suggested by a flat universe to the bubbling chaos of eternal inflation. We have considered the possibility that our cosmos is a single note in a cyclic symphony, or a holographic projection from a distant boundary. Each idea stretches the mind in a different direction, challenging our most basic assumptions about space, time, and existence itself. The true destination of this exploration is not a specific answer, but a transformed perspective. The night sky is no longer just a blanket of stars. It is a living history, a fossilized light show where every point of light is a message from an epoch long gone. And beyond that tapestry of ancient photons lies the true mystery, a contemporary universe we can never witness, filled with possibilities that range from the eerily familiar to the utterly alien. This realization is not a cause for despair, but for liberation. It frees us from the need for a simple, complete picture. The cosmos, in its ultimate nature, refuses to be fully known, and in that refusal, it offers an endless invitation to wonder. The questions themselves become the treasure. Is our universe infinite? Is it one of many? Does it loop back on itself? We may never know for certain, but the act of asking, of building theories and peering deeper into the cosmic microwave background, is how we participate in the grand story. It is how a species on a tiny rock orbiting an average star reaches out to touch the edges of reality. So the next time you find yourself under a clear, dark sky, take a moment. Let your eyes adjust. See not just the stars, but the immense, silent distances between them. Feel the scale not as a cold fact, but as a profound presence. In that moment, you are standing at the shore of an ocean of mystery, connected by the atoms in your body to the very first moments of time. That connection, that capacity for awe, is the most powerful tool we have. It drives the scientist at her telescope, the philosopher with his questions, and the dreamer gazing upward. We hope this journey has given you a new lens through which to see that dark expanse. Which of these cosmic possibilities captures your imagination the most? Does the idea of an infinite universe filled with copies of ourselves intrigue you, or does the elegant closure of a finite, wrapped cosmos feel more compelling? Share your thoughts in the comments below, and let's continue the conversation. If you enjoyed this deep dive into the fabric of reality, please subscribe for more journeys to the furthest edges of science and wonder. Keep looking up, keep questioning, and never lose the humble, exhilarating awe of the unknown.